And we will start the lecture by reminding you that last time we had talked about the unitary time evolution of states. And so the idea here was that if we want to find out what the state ket is, psi of t, at some time, it's equal to a unitary operator, u of t, times the state ket at the initial time, which we're going to call t equals 0. Okay, where this unitary operator, one way of writing it is that you do a sum over all energy eigenstates, and for each energy eigenvalue, you sum over all degeneracy labels. You multiply by a phase factor that's different for each different energy. And then you write what looks like completeness. The only reason it's not completeness is because of that phase factor. Okay, and so that's the construction of the unitary time evolution operator. This is assuming that the Hamiltonian didn't depend on time. We also talked about what happens when it does depend on time, which is more complicated. But this is assuming Hamiltonian is time independent, which we'll be assuming for a while. Okay, so let us apply this to the case of a free particle. And we'll make it a free particle moving in one dimension to make things easier. Okay, and so the Hamiltonian in this case is just the kinetic energy of a free particle, which you can write as the momentum squared divided by twice the mass. So this is kinetic energy. And because it's a free particle, we're assuming it has no potential that it's moving in. And so then the Schrodinger equation is I h bar, time derivative, acting on the ket psi, is equal to the Hamiltonian acting on psi is equal to the operator p squared over 2m acting on psi. Okay, and so to apply the previous unitary time evolution operator formula, what we want to do is we want to find stationary states. Those are the eigenvalues of energy. So stationary states are labeled by energy and a degeneracy label, and they satisfy that p squared over 2m acting on them is going to give back the energy times the same stationary state. And in looking for these, it's a good idea to notice that there's a compatibility issue, because you can also talk about them as eigenstates of momentum. So since the momentum commutes with the Hamiltonian, that's just basically saying the Hamiltonian doesn't depend on position. That commutator is 0. Then we have this theorem that says we can look for simultaneous eigenkets of energy and momentum. Okay, and so in fact, if we think about acting with p squared over 2m, the energy operator, on a momentum eigenket, that's just going to be the number p squared over 2m acting on the momentum eigenket, which is equal to the energy acting on the momentum eigenket. So these are the eigenvalues that have to be equal. And so the solutions of this equation have the form that there's an energy eigenket that I'm going to label right or right moving, which has momentum P equals square root of 2m times the energy. So all of this is within the ket. And then there's a degenerate left moving energy eigenstate, which is P equals minus square root of 2me, all again within the ket notation. Okay, and so right and left here are degeneracy labels. For the energy. The momentum operator does not have a degeneracy, it turns out. Okay, so now we can go ahead and construct our unitary operator for a free particle. U of t is equal to integral from minus infinity to infinity dp of e to the minus I e t over h bar pp. So I'm using p here because that way I don't have to worry about the degeneracy. The momentum eigenstates are also energy eigenstates, but they're not degenerate. I could just as easily have instead integrated over energy, but then I would have had to include two terms, one for these ones and another one for these ones. And so if I just split it up by momentum rather than energy, then I only have to write one pp term. And then there's the phase factor that makes it not equal to just a completeness relation, which would give 1. And then finally, there's this integral. So notice that because momentum is continuous, we have to do an integral rather than a sum. So this is an integral because continuous. Okay, or I can just rewrite this by plugging in for E what it equals in terms of the integration variable, namely P. So this is an integral dp, an exponential of minus I over h bar, p squared over 2m times time. And then I have my p ket p bra. Okay, so that's our unitary operator that does time evolution for us. All right, so one thing we might want to do is we might want to work with in position space with wave functions. And so we can define, for this unitary operator, we can define its position space matrix elements. Okay, so these are the position space matrix elements of our operator U, and they're just x, that's one position eigenket, U of t, x prime. I could have called them x1 and x2 or anything else like that, but this is going to be equal to minus infinity to infinity dp. I'm just going to plug my x and my x prime in here. And then I have my exponential. And so the good thing about this is we know what these inner products are. Each one of them has a 1 over square root of 2 pi h bar, but there's two of them. So that makes 1 over 2 pi h bar. And then I can combine the exponential parts of them to give e to the I p times x minus x prime over h bar, all in the exponential. Okay, so now evaluating this thing is reduced to doing an integral. And we can do the integral by the trick of completing the square. So what that means is you look for a new change of variables In this case, the thing that works is P prime equals P minus M over T, X minus X prime. Okay, and dP prime is dP. And we're using the fact that if we integrate minus infinity to infinity, du, e to the minus u squared, a squared, that's square root of pi over a. Okay, and so now plugging all that stuff in, you can do the integral and you should find x u of t x prime is equal to the following: m over 2 pi h bar I times the time to the 1/2 power times an exponential of I m x minus x prime squared over 2 h bar t. All right, so that's our the matrix elements of our unitary time evolution operator. And so now we can do things like this. We can say the wave function at time t is, well, by definition, it's the inner product of the position operator with psi of t, which is equal to x times u of t psi of 0. Okay, and now to get this in the form where we can use the matrix element, we can use completeness. So we can say this is equal to the integral from minus infinity to infinity dx prime x u of t x prime. Now we're ready to plug in the previous line. And then what goes here is x prime psi of 0. Okay, so I've done completeness by inserting a complete set of states with an integral over them, and that's just one. Okay, and so now we've got the following relation, that the wave function at time t we can obtain as an integral over dx prime of just plugging in our matrix element. It's m over 2 pi h bar I t to the 1/2 power. There's an exponential of I m x minus x prime squared over 2h bar t. And then there's our wave function at the initial time, psi of x prime 0. Okay, so that's the given, is this initial wave function. You assume that somebody has provided for you a wave function at time t equals 0. Okay, and then all of this stuff right here is characteristic of the fact that we're talking about a free particle. Otherwise, it would be something else that would go there that you'd have to work out on a case-by-case basis. Something else goes here in general. And you would get that by going back to what we did here. You would, you'd be always evaluating this thing. Okay, but for different values of the energy and different stationary states, depending on what the problem was. Okay, so this answer that we got is very specific to the free particle. And now we can do the whole thing. And so we just need to do an integral in order to get the answer. So in more complicated situations, the integration might be extremely difficult, but you could always have a computer do it if necessary. Computers are very good at doing integrals. Okay, and so in the end, you get a wave function at a later time. All right, questions on that so far? Okay, so we can do a nice example, which is the spreading of a Gaussian wave function. One of the reasons this is a nice example is you can actually do the integral in this case. As I mentioned, in other cases, the integral might be just too hard and you just have to do it by computer or something, but this one can be done all analytically. So here we're going to start with what we'd worked out before for a Gaussian wave function. Except now we're specifying it, I'm going to specify it as a function of x prime because that's what's going to go into the integral. And I'm specifying that this is at time t equals 0 now. But otherwise, it's just what we had before. It was 1 over 2 pi sigma squared to the 1/4. There's an exponential e to the I p0 x prime over h bar. And then there's a Gaussian part, which is e to the minus x prime squared over 4 sigma squared. So as a reminder, what the various parts of this do, the last part here is telling you that the expectation value of the operator x in this state is 0. The uncertainty in x is sigma. And the uncertainty in the momentum is h bar over 2 sigma. That's what that part of it does for you. This part of it just shifts you in momentum and says, even though the uncertainty in momentum is the same, the expectation value, instead of being 0, because of that factor, is p0, as you worked out for homework. And then in a more general situation. And then this other part here is just the normalization factor to make sure this thing is normalized to 1. And then as a reminder, we were guaranteed by unitary time evolution that if it was normalized to 1 to start with, it will be normalized at all later times, as long as we don't make a measurement in between. If we make a measurement in between, then we have to renormalize the wave function. Okay, and so if we graph as a function of position, what is the square of this wave function? It looks like at time t equals 0, it's a Gaussian. Okay, and it has width proportional to sigma, and the whole thing is supposed to be moving to the right with momentum p0. Okay, so our expectation, which we will try to work out from the formulas, is that this will move to the right. And it will also spread out as it goes. Okay, so let's see how that happens. So basically, we just need to plug this into our formula. Psi of x and t is going to be equal to, so first of all, there was a factor of m over 2 pi h bar I t to the 1/2.
Yeah, was there an h left out in that top one, or am I mistaken?
H left out.
The last exponential? Or no?
The last exponential? I think that's okay.
That didn't need an h?
No.
Okay.
I don't think.
Well, where did you get the expectation p off of that from?
Oh, so you're talking about this factor.
No, the next one. Yeah.
Right. So that we had worked out the other day when we studied just this wave function. And
Oh,
so we had plugged that in and worked out what the momentum so if you forget this part for just a moment, when we worked out the expectation value of p, it was 0. And then we worked out the expectation value of p squared and took the square root, and that's where this came from. Okay? Good. Okay, so getting back to this, there was this factor, this to the 1/2. There's our normalization factor. I'm going to write all the constants out front because they're not part of the integration. Okay, and then there was an integral that we have to do, minus infinity to infinity dx prime. Okay, and then we need to plug in our x prime wave function, which is exponential of minus x prime squared over 4 sigma squared, plus I p0 x prime over h bar. And then there was another part of the exponential that came from the unitary operator matrix element, which is im x minus x prime squared over 2 h bar t. Okay, so there's an integral that has to be done, but notice that once again, it's the exponential of something quadratic. And so you can use the trick of completing the square. And so I'll just write down the answer here. This is equal to 1 over a square root, which also has a square root of 2 pi within it. And then there's sigma plus I h bar t over 2m sigma. Okay, then there's also an exponential that turns out to be minus x minus p0 t over m, all squared, divided by 4 sigma squared, plus 2i h bar t over m. It's kind of a mess. And then there's another exponential left over, which is I p0 over h bar, x minus p0 t over h bar. Okay, so one thing to notice about this is that its dependence on x always comes with x minus p0 te. Oops, I think this should not have been an h bar. Sorry, this should have been a, let me erase this. So this is actually over 2m. Okay, so we have two different combinations of x minus the momentum times time. This one has x minus momentum times time over 2m. And this one has just x minus momentum times time over m. Okay, so it turns out this one right here is a phase, and so it's going to be not so important as this one, which contains a Gaussian factor. Okay, so in fact, to make that a little bit clear, we notice that the first exponential actually is complex, and that's annoying. So we're going to use the fact that 1 over a plus ib, where a and b are real numbers, can be written as a minus ib over a squared plus b squared. That's for real a and b. We're going to use that on this exponential. Okay, and so here I'm going to be skipping some annoying steps of algebra that aren't very illuminating. I'm going to write the answer as e to the I times a phase factor that I'm going to call theta, divided by the same square root of 2 pi, sigma plus I h bar t over 2m sigma. And then the only thing left over is an exponential now of a real quantity, which looks like x minus p0t over m squared over 4 sigma squared plus h bar squared t squared over m squared sigma squared. Okay, and now all I need to tell you is what was that theta thing. Okay, and the algebra is a little bit painful, but in the end, you get theta of x and t turns out to be p over h bar x minus p0t over 2m plus h bar t x minus p0t over m all squared over 2m 4 sigma squared plus h bar squared t squared over m squared. Okay, so it's a little bit complicated, but the main point here is this is a phase. And so things that I do where I end up squaring, taking the complex square of the wave function, are not going to depend on that. So in particular, for example, I could ask, what's the probability density to find my particle at some position? Okay, so the probability density is just the wave function squared. So that's psi of x and t squared. Now the theta thing is just irrelevant. And this is 1 over square root of 2 pi sigma squared plus h bar squared t squared over 4m sigma squared times the exponential. But since I'm squaring it, basically the exponential just gets multiplied, the argument of the exponential gets multiplied by 2. So this is x minus p0t over m squared divided by 2 sigma squared plus h bar squared t squared over 4 m sigma squared. Okay, so what did we find out here? We found out that at time t later, this Gaussian wave packet, or the thing that started out as a Gaussian wave packet, is in fact still a Gaussian. It's just that its center has moved to p0t over m. Okay, and so this is Gaussian wave packet at time t. And it now has expectation value of position equals the momentum times time over mass. That's classically what you would expect for a particle moving to the right. Okay, and furthermore, because this thing is just exactly what we had before, except with sigma squared is now replaced by this more complicated sigma squared plus h bar squared t squared over 4m sigma squared, we can just plug in what we had before to find out the uncertainty in x. The uncertainty in x is just this, sigma squared, square root of sigma squared plus h bar squared t squared over 4m sigma squared. Okay, so at time t equals 0, it just reduces to sigma, which is what we found before, and it spreads out. It gets larger as t increases. And in fact, at late times, it gets very large. Okay, so at late times, I can just ignore the original constant value compared to this thing that's getting very large and just take the square root of it. And so at late times, the uncertainty in x is going to be approximately just h bar t over 2m sigma, which is ironic in the sense that if I start with a very small sigma, because at late times I'm dividing by sigma, that means this thing will be more spread out at late times if I try to make it less spread out at earlier times. So ironically, larger delta x at large t if you try to make it be small, so small sigma, which means that you had delta x small at t equals 0. So the idea there is if you try to make the wave packet very confined to a small region at very early times at t equals 0, then your momentum could be anything. And so it has a high likelihood of spreading out super fast at late times. Okay, and then another check that's good to do is that 1 is equal to minus infinity to infinity dx of psi of x and t squared. This was the promised fact that if it was normalized to begin with, it stays normalized as long as I don't make a measurement. This is independent of t. And it's also 1, which means probability is conserved. So probability conservation is built into unitary time evolution. All right, any questions about that before we move on? Okay. So now we're going to talk about specific problems that are more complicated. For example, the case of a particle in a 1D potential. Okay, so now we're going to be considering a Hamiltonian that's p squared over 2m plus a potential v that's a function of the operator x. But for the moment, we're going to leave this unspecified. We won't say exactly what it is until we have to. So I should say for now. Okay, so what's the idea here? In order to understand the time evolution, what we want to do is first construct the stationary states, because if we've got those, then we can construct the unitary time evolution operator, and or we can just evolve the stationary states individually. So look for stationary states. And stationary states just means energy eigenvalues. So that means we're trying to solve the problem p squared over 2m plus v of x, whatever it turns out to be, acting on the state psi that I'm going to label with an energy label, E, is equal to the number E, which is guaranteed to be a real number, because these are Hermitian, Hamiltonians are Hermitian operator, times E. And our strategy here is going to be go to the position representation and what those words mean is the following. First, you take the inner product with the bra, which is a position eigenstate. Okay, and then if you do that, the operator x is represented by the real number x. The operator p is represented by minus I h bar d by dx. Okay, and the ket psi sub e is represented by the wave function x psi sub e otherwise known as psi sub e of x. Okay, so all of those things are what we mean by go to the position representation. Okay, and so if we do that, this differential equation becomes 1 over 2m minus I h bar d by dx squared, because it's p squared, plus v of x. Notice I'm writing this as a lowercase x now, acting on the wave function ci psi e of x is equal to e psi e of x. That's a second order differential equation, and so let's put it in a standard form by just isolating the derivatives. Okay, and so this is second x derivative acting on psi sub e is equal to, moving everything else to the other side of the equation, 2m over h bar squared times the potential minus the energy eigenvalue acting on psi sub e again, or multiplying psi sub e again. Okay, so that's our differential equation that we want to solve. And we need to, this is the time independent, because there's no time in it, Schrodinger equation. Okay, and the idea is we need to solve this self-consistently for the wave function and the energy simultaneously. Okay, so for E and psi sub E, which is a function of x. Okay, so that's going to be our task for several weeks now in the future. And before doing that, let's see some things that we can say about the wave function we're trying to solve for. And from now on, I'm just going to drop the subscript e. It's going to be understood that I'm talking about wave functions that have a specific e. Okay, so what can we say about the functions? I'm going to make some general statements about psi of x. So the first thing is, this is a mathematical statement that follows from the physics, and that is that the wave function should be continuous, always. Okay, and why should it be continuous? It's continuous because I know if I take its complex square, I'm going to get the probability density. And physically, I should be able to unambiguously say what the probability density is. And that's the definition of continuity. So the probability density, from a physics point of view, should be unambiguous. Okay, which means psi squared is unambiguous, which means that psi is unambiguous. Okay, now you could mathematically maybe construct wave functions that don't satisfy this property of continuity, but what this is saying is those aren't physically meaningful, and as physics people, we don't care about them. So if it's continuous, then you could ask maybe the first derivative of psi is continuous. I'm putting a prime on this to continuous to indicate the first derivative. Okay, and I'm going to put a question mark there because it turns out sometimes it's true and sometimes it's not. So let's consider a point where it may or may not be continuous. So consider a point x equals x0. So in order to understand whether this wave function's first derivative here is going to be continuous, what we can do is integrate both sides of the Schrodinger equation. So this is a very standard trick. We're going to integrate from x0 minus a little bit to x0 plus a little bit with respect to x. And so that looks like x0 minus epsilon to x0 plus epsilon. The left side of the Schrodinger equation is the derivative of a derivative, otherwise known as a second derivative. And here's the right-hand side, 2m over h bar squared, x0 minus epsilon to x0 plus epsilon, v of x minus e times psi of x dx. Okay, now, suppose that the potential isn't doing anything weird near x0. So for example, let's consider that it's finite there. Then when we do this integral, we're just integrating a finite number times a continuous function, psi of x. And so nothing weird is going to go on. And then when I take epsilon goes to 0, this thing is, the whole right-hand side is just going to get very small. So this is going to be of order epsilon if v of x isn't doing anything weird, in particular if it's finite. Notice I'm not necessarily assuming it's continuous, just that it's finite. So not necessarily continuous. It's still, even if it's discontinuous, as long as it doesn't get super big or diverge, then the right-hand side is going to be of order epsilon. On the other hand, the left-hand side, by the fundamental theorem of the calculus, the integral of a derivative is equal to psi prime x naught plus epsilon minus psi prime x naught minus epsilon. Okay, and so as long as v of x was finite, then psi prime of x is continuous. That's what the left-hand side is saying. The left-hand side is very small as epsilon goes to 0. Okay, now we have to worry about, though, what happens if the potential blows up. And this is not just a trivial thing, because remember, for example, in the hydrogen atom, that's a 3D problem, so it's a little bit different, but the potential does blow up, in fact. So potentials don't have to be finite. And so one thing you can ask is, what if, for example, it has a delta function? So here we're assuming that it's got a delta function at the point x0 that we're worried about. And then maybe it's also got a finite part that's not going to be very important for us. What's really important is the fact that it's trying to blow up. Okay, so then we can do the same thing that we just did. What will change is that now we have psi prime x naught plus epsilon minus psi prime x naught minus epsilon. Okay, but now the integral looks like this. Okay, the finite part doesn't matter, of the potential doesn't matter, but the delta function part can give a non-trivial answer. And so I'm including that. And in fact, the definition of the delta function tells us what this integral is. This integral is nothing other than c times psi of x0. Okay, so that's not 0 as epsilon goes to 0. And so what we've derived is, in this case, there's a discontinuity in the derivative of the wave function. Okay, so in that case, psi prime of, I'm going to write it x0 plus, that's the same thing as x0 plus epsilon. It just means x0 plus a tiny bit, minus psi prime of x0 minus a tiny bit, equals 2m over h bar squared times the c that went in the potential times the value of the wave function there, which again is unambiguous because the wave function is continuous. It's the first derivative that has a discontinuity. So this is telling you the discontinuity in the first derivative of the wave function. Okay. So another thing that can happen is maybe you don't have a delta function, but maybe the potential is going to infinity anyway, and is infinity on one side of a boundary. So what if v of x equals infinity for all x less than x0, and it's finite for all x on the other side of the boundary, so x greater than x0. So this infinity corresponds to the particle being forbidden to ever go there. It would cost an infinite amount of energy to do so. And finite means the particle is allowed to go there, at least in principle. Okay. Then, if the particle is forbidden to be there, that means that its wave function must be 0. It has 0 probability of being there. That's going to be true for x less than or equal to x0. And notice that it's less than or equal to, not just less than, because it has to be continuous. And then you can reverse the inequalities. If it's anytime it's forbidden to be in some region, then also on the boundary of that region, it has to be forbidden to be there. Okay. So finally, we can talk about things that behavior of wave functions at infinity, and there's the concept of bound states, which we've actually mentioned before, but now we're going to talk about them again. So bound states are things whose wave function goes to 0 for x getting super large or super small. So x going to plus or minus infinity. So here's a statement we can make about this, that in one dimension, and it's very important, this is only true in one dimension, the energy eigenvalues for bound states are never degenerate, which is a useful thing. For the free particles are not bound states, so we had a double degeneracy. But here, the claim is they're never degenerate.
Is there a reason for that, Professor?
Yeah, we're about to prove it. Okay, so here's the proof, and it's by contradiction. In other words, we're going to assume the opposite and prove that that will fail. So suppose you had two different wave functions that both satisfied this Schrodinger equation with the same eigenvalue. So I'm going to call one of them psi1, and the other one psi2. And notice I'm giving them the same energy eigenvalue. I'm assuming they're degenerate. Okay, and now we're going to take those two equations. We're going to multiply first equation by psi2 and the second equation by psi1 and take the difference. When you're doing proof by contradiction, it's always the strategy of you write them down and then you take the difference. In this case, it amounts to just psi2 psi1 double prime minus psi1 psi2 double prime equals 0. Because when you take the difference, the rest of this just cancels out, which is convenient. Okay, or we can write this as, it turns out, d by dx of psi2 psi1 prime minus psi1 psi2 prime equals 0. That's a total derivative, and it's just begging us to integrate it because it's a total derivative. Who are we to deny it? So let's integrate it, and we get psi2, psi1 prime minus psi1, psi2 prime equals, when you integrate, you get a constant of integration that we have to worry about. But now we get to use the fact that it's bound states. Psi2 and psi1 are both equal to 0 at x equals plus or minus infinity. Okay, which means that this constant can only be 0. Because we know that it doesn't depend on x, so if it's 0 at infinity, it must be 0 everywhere. So we've learned that that's 0, and so we've learned that psi1 prime over psi1 equals psi2 prime over psi2. Or another way of writing that is d by dx of logarithm of psi1 equals d by dx of logarithm of psi2. Now again, it's a total derivative. So let's integrate again. Total derivatives love to be integrated. Okay, and so now we get log of psi1 equals log of psi2 plus maybe another constant of integration. We'll call it k this time. So this is another constant. And now we can exponentiate. Okay, and so what do we get? We get psi1 of x equals e to the k psi2 of x. So what does that say? That says our two wave functions, which we were assuming were different, are actually proportional. And one of the postulates of quantum mechanics says if you have things that are proportional with a constant, that makes them the same state. So what we've just shown is that assuming that they had the same energy eigenvalue and that they were bound states in one dimension so that we could do these integration tricks, then they're actually the same state, and so there's really no degeneracy. Okay, so again, this does not work in three-dimensional bound state problems. And in fact, in three-dimensional bound state problems, there are lots of energy degeneracies, as we will see. But it's going to be a useful thing to apply this when we studied one-dimensional problems, as we will do, starting next time. Okay, so sorry I went over a little bit. You all should have gotten, late last night, I emailed your graded homework problems back. And later this afternoon, I should be sending out the homeworks. So you should look forward to that. Okay, are there any questions?
I still have a few questions from the text.
Sorry, from what?
From the book, from your notes.
Okay. So maybe I'll stop the recording and let people who want to go